Okay. Okay. So good morning. We start the second day of our meeting.
Morning, everyone. My name is Agnieszka Świerczewska-Gwiazda, and it's a great pleasure for me to introduce the first speaker. So, if I wanted to say a couple of words about Tomasz Dębiec, well, the first thing is, I would say, a great friend of mine, and whom I can always rely on, and we share lots of common interests and common sense of humor, And the second thing that I can tell about Tomek is that he's my former PhD student, and Tomek came to the University of Warsaw after studying at the University of Warwick. Even though he didn't work there so much in PDEs, mostly in topology, but he just jumped into the topic and started to work, and that's how it started. So first, it was mostly fluid dynamics, and what we can say that in fact now we are experiencing the golden age of fluid mechanics and PDEs in fluid mechanics, because we are now witnessing, in fact, lots of great things that are happening, lots of new results, and what I can surely tell about Tomek, that he's not only witnessing it, but he is a part of that. So the result of Tomek really are important for the whole history that is creating now. And later also Tomek started with, he's always happy to travel somewhere, and not only travel, but also to work hard with people. So Tomek also started with the topics of math biology, math biology in such a really novel setting where one uses methods of mathematical physics and really delicate issues in PPEs. And I think we are going to listen about it today, and Tomek will talk about conserved quantities and regularity in fluid mechanics, and I don't know, will you mention also about math biology problems? Not today. So I encourage you to listen to some other talks of Tomek on some other occasion. Okay, good. The floor is yours.
Thank you very much, Agnieszka. Very kind introduction. Yes, so what I'm going to talk about is not the full title of my thesis, and as Agnieszka mentioned, there are other things I've been investigating, but today I want to focus on the things that I started with. And actually, these are the things that I started with actually here at the Banach Center, because I've been introduced to the topic that I will be describing during a Simon semester that was happening here. So that was a great opportunity for me to start my PhD. And in particular, I met my first international collaborator here upstairs in the common room. So it's a nice thing that I can speak about these things now here. And since this is a special occasion, I want to start also with oh, this doesn't work again. Sorry. With a very personal first slide. So obviously, I'm very much in debt to Agnieszka for being a great supervisor during my PhD and later on. So yeah, yesterday at dinner there was some conversation about the importance of the advisor for a PhD student, and Agnieszka is a perfect example how important that is, and she's still a role model to me. So thank you. Okay, so to business. I will be talking about conserved quantities, and really what I mean by that for the duration of the talk is going to be energy, okay, in some physical systems. I will be talking in particular about some equations, probably the most or the second most famous equation of fluid mechanics, and the problem of whether solutions to this equation conserve energy or not. Okay, so whether you work in PDEs or not, if I tell you that conserved quantities are important, you will probably think, yeah, sounds about right. Should make your life easier if you have some quantities that are conserved. And you'll be totally right, because yes, unsurprisingly, they play a very, very important role in the analysis of nonlinear PDEs. In particular, for instance, I mean, from an analytical point of view, oftentimes they are the only source of a priori information that yields sufficient compactness to even start the analysis, to even prove any existence results. That's, for instance, the case for the Navier-Stokes equations. And if our life was easy, then, well, I wouldn't be here, but, and if we were just talking about smooth functions, which really do satisfy the equations I'm going to show you in a minute, in a pointwise sense that you can actually differentiate and apply some calculus rules to, then it will be very nice and easy, because you can usually derive some nice properties of those solutions, but this is not the case. And indeed, from the physical point of view, you do observe that those quantities that formally or for very smooth solutions are conserved, they can be dissipated. So that's sort of the issue of my talk. Even then, though, even if those formally, even if on the formal level, some quantities are dissipated, then still it's rather important to know whether some expected balance will be true as an equality or not. That's again, for instance, the Navier-Stokes, the very famous Navier-Stokes equations. It's one of the key questions. Okay, so we do have this sort of dichotomy that sometimes there is conservation, sometimes you can think of low regular solutions which will not satisfy some expected conservation laws. So this motivates the question of when the breakdown of this law happens. Okay, when it's true. Okay, so here's the main player, the main system of what I'll be talking about. So this is the incompressible Euler system, and it's supposed to describe a flow of an inviscid incompressible fluid, okay, with constant density, which I, without loss of generality, assume to be 1. Okay, so the first equation there is the conservation of momentum. So this is due to the second law of motion, which says that the acceleration of a fluid particle is proportional to the pressure force acting upon it. Okay, and the second equation is the incompressibility condition, which says that the volume of any part of the fluid is constant along the flow. Okay, and below you have the notations that I'm using. Hopefully these are not debatable. And while I acknowledge that the most important and the most fascinating phenomena that happen in real life are due to the presence of physical boundaries in the domain, I will only stick to the simplified case of the periodic box, because, well, I need a manageable mathematical setting somehow. So in general, whatever I'm going to tell you about extends to the whole space without much problem. If you want real boundaries, really interesting things start to happen, and it's something that one has to really focus on. Okay. So this, just to give you a quick idea that it's not an easy system to analyze, mainly because this transfer term, the second term in the conservation of momentum, which is sort of saying that the fluid is the velocity is transported by itself, generates a nonlinearity, which, as we know, is something that makes our lives difficult. Okay, so despite this equation being written down in 1755 by Euler, and in fact being, I think, the second partial differential equation ever to be written, second only to the wave equation in 1D, we still don't know very much about it. So in particular, one huge question is about global and time existence of smooth solutions. Okay, it is classical by now that we have local existence, so there is a small time for which there are smooth solutions, but whether they stay defined for any time or whether there is a blow-up is still an open question. In 3 spatial dimensions and higher, in 2D, we actually know about global existence. Okay, and this the problem of existence may be due to possible formation of singularities in the vorticity, and this is the object of this famous Beal-Kato-Maeda criterion, which specifies what happens at blow-up time. Okay, there is there's a nice property which says that, okay, we don't know whether strong solutions exist for any time, but at least we know, and I will relax the notion of solution in a minute, so at least we know that they are unique in a larger class of solutions, of generalized solutions I will talk about in a minute, but I will not actually talk about this last point very much. In principle, any of those points can make a nice set of lectures in themselves, but that's just an overview. Okay, so the main calculation of today is this very nice property of strong solutions. So if I take a C1 function, which actually satisfies the Euler equations in a pointwise sense, and I multiply the momentum equation by the velocity, and by multiply I mean taking the scalar product. So I'm getting a scalar equation, and then I get what you see here. Okay, upon using the chain rule for the time derivative term, and for the convective term, I'm using the product rule over here, and the chain rule to write it as so. As you can see here, and for the last term I'm doing nothing. And then when I integrate in space, and I integrate those last 2 terms by parts, and use the incompressibility condition, I arrive at this conservation of kinetic energy expression. Okay, and if you further integrate by in time, you will see that the kinetic energy at any time t is equal to the initial kinetic energy. Okay, there's a typo here, so that should be the torus. Okay, so that's all nice and pleasant, but as I said, our life is not unfortunately so simple. In particular, I do need regularity. Okay, I do need regularity to integrate by parts, to use the chain rule, and so in a sense, there is 2 ways you can interpret my talk. You can think I'm talking about turbulence, or if you're inclined this way, you can think of whether I'm talking about the breakdown of the chain rule for non-differentiable functions. Okay, and this is somehow the topic. Okay, so just quickly to say about weak solutions. So it is a common occurrence in the theory of partial differential equations that you can't really directly construct classical solutions. So you can't find a C1 function V that satisfies the Euler equations. As I said, this is a huge problem. Okay, so what one does is one relaxes the notion of a solution. Similarly, as functions are generalized to distributions, I will be talking about distributional solutions So if you had a smooth solution of the Euler equations, this equality would certainly be true just by integrating by parts the derivatives onto some test function. And instead, we will now take this equality to be the definition of a solution. Okay. So just as in distributions, so you put derivatives away, you do so also here. And the immediate consequence of that is that now I don't need my solution to even have any derivatives well defined. Okay, it's enough if it's an L2 function. It has to be L2 because I'm multiplying v by v, but nothing about the derivatives. Okay. And similarly for the incompressibility, I formulate it in a weak sense. And then one might hope that since we're relaxing the notion of a solution, then the question of existence should be easier because I'm looking for a weaker object in a sense, but uniqueness will be harder. And then one might hope, if one is lucky, that one will be able to show that such defined weak solutions will be unique and will have additional regularity that you can show a posteriori, I'm sorry, to recover classical solutions. And this is indeed, sorry.
Sorry, I didn't want to interrupt, but maybe I missed, why are we on, where did the torus come from?
Oh, sorry, this is the spatial domain for my equations.
Like something flowing on a torus.
No, it's imagine a box that is periodic in space. It's a Euclidean R3.
This is like to deal with non-compactness possibility of your.
It's imposing periodic boundary conditions in a sense. So what it does for me in practice, for instance, is that it allows me to integrate by parts without wondering about any boundary terms and so on. But there's no funny topology going on or no manifolds behind this. Okay, so one example, the main example of this strategy that I just mentioned of going from weak solutions to classical solutions, and that's the success of this strategy, is linear elliptic systems. Okay, unfortunately for the Euler equations and for most or any equations in fluid mechanics, this is not the case. And in fact, when I say that showing uniqueness for weak solutions is difficult, for the Euler equations, it turns out it's difficult because it's just not true. They are not unique, as you will see in a minute. Okay, there's a remark about the pressure, but let me skip that. Just forget the pressure. Okay, in the incompressible Euler equations, the pressure is just a Lagrange multiplier that is there to guarantee that the incompressibility condition is satisfied. I will talk more about the pressure for the compressible case, if I manage to get there. Okay, and so as I said, the motivation here is smooth solutions satisfy energy conservation at low regularity. I don't know how to justify the computation I've just made, so perhaps there is some breakdown. And this is known, for instance, for compressible fluids. We know for a very long time that there are shock waves which do dissipate entropy, mathematical entropy. This is to be expected in a sense. And indeed, this is the object of a very famous conjecture, a theorem now, but it's still fresh somehow, so people do still say conjecture. Which was postulated by Lars Onsager in 1949. And in mathematical terms, although it was, in fact, in Onsager's note, it was formulated very much like this. So if you consider weak solutions of the Euler equations, which are Helder continuous, okay, with exponent theta, uniformly in time, then if theta is large enough, larger than 1/3, then the energy will always be conserved. And for any exponent less than 1/3, you will be able to find a weak solution for which this is not true. Okay, this is a very striking thing. And so you might wonder, given what I've just told you about regularity and integration by parts, that why would Onsager, who was a physicist and Nobel Prize laureate in chemistry, why would he be interested in the breakdown of the chain rule? He wasn't. So he was motivated by the theory of turbulence. So in fact, really, he was interested in the Navier-Stokes equations when the viscosity tends to 0. And then the so-called energy cascade that makes the conservation of energy in the limit not true.
This is in the development dimension, or the dimension is 3?
Oh, I'm sorry, I'm jumping between dimensions. This is true in any dimension, but think of t equals 3 for most of the time.
But the 1/3 is independent of dimension.
It is, yes, it is independent.
So there's,
It's not 1/d.
there's an easy intuitive argument for 1/3. How Onsager got the 1/3?
Yes, the easy argument is if you look at the, I don't have the integral. I have chalk. So you have this term when you compute the energy argument. You have this term which is u times gradient u times u. Okay, and this is due to the convective term. And in a sense, okay, this is very formal and heuristic. If you thought of the gradient operator as a multiplication operator, you could sort of split it in 3 equal parts and distribute it onto the other u's that appear here. And this is somehow the behind this. This is why, in fact, when speaking about the solution of the Onsager conjecture, Fourier methods are used a lot, because somehow behind there is this idea of thinking of the differentiation operator as a multiplication. There are other heuristic arguments which justify that, but that's. I mean, Onsager's one was similar to this, based on Kolmogorov's theory, but in essence, it's due to that. But in my very last slide, I will actually say that maybe the relation with turbulence is not so clear, but that's to come. Okay, as I said, this is now a theorem. The first part was proved in the 90s by Konstantin and Titi, and I will actually give you a proof because it's very simple and nice. And the other part was the thing that really made this popular in the last already almost 15 years. So it started with the constructions, with the development of the so-called convex integration techniques. In this context, they've been known before, but in this context. Okay, so what does it mean for those weak solutions which don't conserve energy? So this is not new. It's not that the resolution of this conjecture showed us first examples of weak solutions which do not dissipate energy. This has been known.
I have a question. Can you go to this Onsager theory?
Yes.
What happens if theta equal to 1?
Yes. Well, this is delicate. It's the short answer is it's not known. Like for really theta equal to 1/3, but there are results in this direction. For instance, there are solutions which belong to the intersection of all Helder spaces with exponents less than 1/3. There is you have to look very closely at some logarithmic scales. Okay. So this is sort of still open in this particular So the first example of non-uniqueness was due to Scheffer, who constructed a weak solution in L2 with a compact support in space and time. Okay, and this is, if you think about it, this is mental, right? Because it's what it means is you have a glass of water, which is like this one here. I didn't plan this, and then suddenly it's develops some sort of tempestuous behavior, and then something happens in it, and then after a certain time, it becomes still again. That's what this is saying. So of course, this is non-physical. On the other hand, the important thing, maybe I should mention about Onzager's motivation in turbulence is that those solutions that I will be talking about from now on are not always just some mathematical topologies. Okay, they're really expected in turbulence, and they are something which is observed experimentally. So it's not that I'm talking about some weird things that happen just in mathematics. Okay, so this of course shows non-uniqueness because you can find another solution which is as it should be, and there was another example by Schnirelmann, but these are honestly very, very difficult to read. These papers are almost illegible. But these examples have been recovered and improved on in a very different setting by Delelis and Sekelegidi. And this is this result here is really what started the whole approach towards the full Onzager's conjecture. Okay. So what they used is they adapted this technique, which is now called convex integration, which reaches really to the methods of isometric embedding theorem of Nash and Kuiper, and then also the constructions of Müller and Schwerak for elliptic systems. And I will explain this in a very short slide in a minute. So what they showed is that there is initial data for which there exists infinitely many compactly supported weak solutions to the incompressible Euler system in any spatial dimension greater than. Okay, and this is a very, very nice and elegant proof. It's very geometric and traceable. Okay. And this began the whole story. It triggered a series of papers which started to construct more and more precisely, more and more regular weak solutions to the Euler equations, which didn't satisfy energy conservation. Okay, so started with exponent 1/10, then 1/5, then finally 1/3, but in a slightly different scale of space, spaces. So with L1 in time rather than an infinity, and so on and so on. It was really exciting to see this going on. Okay, in particular, what this technique also allowed was to show that for any initial data there are weak solutions. So it actually led to the first construction of general construction of weak solutions to the Euler system. There is one very important drawback of those solutions, which is that they are not admissible in the sense that they do not satisfy the energy inequality. So there's a very artificial jump of energy at time zero. So if you have the energy of your initial state here, then those solutions, what they do, they immediately jump, and then the energy that goes down. In particular, this doesn't contradict this weak strong uniqueness property that I mentioned. Okay. So the situation is really even worse, because somehow we might think, okay, here you have this anomaly with the jump. So maybe, and people thought that maybe if you impose some admissibility, some selection criteria, then you can recover uniqueness by saying, okay, if my solution actually satisfies a priori the energy inequality, then maybe it doesn't dissipate it. It doesn't do crazy things. Okay. And what subsequent work of Delays and Sekelichidi showed is that it's not true. Okay, so what these three bullets are saying essentially is that any sort of reasonable energy inequality you want to impose is not helping. And even worse, so this says that there exists initial data that do that. In fact, what was later shown is that the set of such data is dense in L2. So somehow this is even generic. Okay, very quickly about this, the idea. I will really not go into the details, but just to give you two main points. So as always, or maybe not always, but as often when a breakthrough happens, it's because someone thinks of a slightly new way of looking at a problem. So the first step is to reformulate the Euler equations. Okay, so rather than looking at it as a nonlinear system, think of a linear system. So replace all the nonlinearities in the system by new unknowns, and then impose some pointwise constraints. Okay, this is just a very, very straightforward reformulation. And then what one does is one relaxes the problem. So rather than looking for solutions which really solve the Euler equations, one allows for some room. Okay, so, and this is called a subsolution. So a solution which satisfies the inequality rather than the expected equality is a subsolution. And the breakthrough was possible because for many systems of fluid mechanics, it turned out that it's much easier to construct subsolutions than solutions. And then you can make the machinery work. Okay? For Euler, in fact, constructing a subsolution is trivial because you can start with zero. And the main point is to keep adding high frequency oscillations to your subsolutions, creating something which in the limit is very irregular, but satisfies the initial problem. I'll skip the details. Okay. Okay. Now about some positive information. So if you have enough regularity, so more than 1/3 of a derivative, then you can restore energy conservation. And this is done by a two-page argument. And it's done by smoothing, by modification. So you take a standard modifier, convolve the equations. So modify the equations. Okay, this is maybe a bit vague, but it can be made precise. But imagine I'm looking at I'm multiplying the equation by the modifier and integrate. So I get this equation. And of course, the main problem is that I have a nonlinearity which doesn't commute with the convolution. Okay, this is the source of all problems, essentially in nonlinear PDEs. Nonlinearities do not commute with modification, and they do not commute with weak limits, and this is why we are here. Okay, but when you do so and rewrite this tricky term in a way that I would like it to look like, I produce an error. Okay, this is called a commutator error. And now, having this equation for the smooth quantities V epsilon, I can redo the argument that led me to energy conservation for smooth solutions in the first place. Okay, and this means that I will have to deal with this error on the right-hand side. And the question now is precisely under what conditions does this error vanish in the limit? Okay, and the idea of Konstantin and Titi was to observe that it can be rewritten. Okay, so this product of smoothed velocities minus the smoothing of the product can be rewritten as a product of the differences, plus a slightly different similar term, which can be treated in exactly the same way as here. Okay, and for the first one, you just use Hölder's inequality. Okay, L3, L3, L3. You end up with this. And now it's just a matter of the simple properties of Hölder continuous functions, which guarantee that these quantities are controlled in this way. Okay? And when you put those together, you end up with the 1/3. Okay. So it turns out that for this positive part of the conjecture, Hölder spaces are not the only space, not the optimal functional space setting in which you can do this. You can extend it to Biesov spaces, and I only mention them because it's relevant for the next couple of slides. But just think of the definition of a Biesov space as being spaces for which you control the shifts in the function in such a way. Okay, this is precisely what I need for this modification argument. Okay, so of course there's a half dozen different ways to define those spaces, and they are really important in PDEs because they give you right scalings in a variety of settings. But for us, let's just think of them as being the analog of Hölder spaces, only LP based in a way. Okay, and it's true that they satisfy also these bounds as well. Okay. So let me move on to the compressible case now. So it turns out that given these new techniques, given convex integration and also the interest, sort of rekindled interest in Gonzaga's conjecture, people started thinking maybe this is also applicable to other systems of fluid mechanics. And it turns out that for the compressible Euler system, which is this system here, where you have again momentum conservation and then mass conservation in the second equation, the continuity equation. Only now the major difference is you have non-constant density, and also you have the pressure, which actually plays a major role in the sense that it's given is a function of the density. So it's an extra nonlinearity in the system. Okay, for me this will always be rho to the power gamma. Okay, so this isentropic power state. Of course, as for any system that comes from physics or mathematical physics, it's true that there should be some energy equality associated to that, at least formally. And you derive it very similarly to what I've done for the incompressible Euler. So you multiply the momentum equation by the velocity, by the solution, you integrate in space, and you use conservation of mass to end up with this equality here. So here you have the kinetic part of the energy plus a potential part due to the pressure. Okay, and even a non-local version is true if you skip integration in space. Okay, and I've mentioned shockwaves before. This is something classical that even starting with smooth initial data in finite time, solutions can develop discontinuities, and in particular, such solutions will not satisfy this equality or this equality. Okay, they will only satisfy an inequality in the sense of distributions. Okay, but it turns out also that more complex mechanisms are possible, as is exemplified by this convex integration technique. Okay, and it started already with the very second paper of Delelis and Sekelichidi, and I will mention that in a second. Okay. So given again here the possibility of conservative and non-conservative solutions, the Gonzaga question is somehow valid for this case as well. Even though the existence of non-conservative solutions is not really an issue because it's been known for a very long time for hyperbolic systems. Okay, and here's here's a first result in this direction, which is due to Fajrajzel, Gwiazda, Agnieszka, and Emil Wiedemann, who say that analogously to the incompressible Euler case, if your solution is regular enough, then the energy is conserved. And by regular enough, I mean, those Biesov spaces, which are analogs of Hölder spaces. If you take alpha and beta equal, you will recover this 1/3 exponent. So you can think of alpha and beta equal. But of course, the whole game here is that having now two unknowns, there is an interplay between them. And you can use the equations to somehow shift regularity between them up to some point. And that's still being investigated, actually, to some extent. Okay. One very important comment about this result is that there is a restriction here in this red line, which says that the method that they use is very similar to the method of Konstantin Netiti, which is to smooth and to consider commutators due to the nonlinearities. And now you have a new nonlinearity because of the pressure. And to deal with that, you have to guarantee that your nonlinearities are C2 with respect to in the range of the density. Okay, and this in particular forces you to either assume that this exponent gamma, the adiabatic exponent, is larger than 2, or you have to exclude vacuum. So you have to assume that your density is bounded away from 0. And the problem is for weak solutions of compressible Euler, it's not clear that you can guarantee this condition even if it's satisfied initially. And also the range of gammas between 1 and 2 is physically relevant. For instance, a monatomic gas has the exponent 5/3. A diatomic gas has 7/5. These are less than 2, so it's really a physical range that one wants to know about. Okay, and this is what I've been doing with Ibrahim Akramov, Jack Skipper, and Emil Wiedemann at that time in Hanover. So we wanted to remove that condition in a way. Okay, and here's one cheap way to do it. So if you assume something extra about the velocity, this is true. Okay, it's the previous theorem is still true if you assume something more about the velocity. In particular, for us, we came up with this bounded measure, divergence measure condition, which is something which is known in hyperbolic conservation. Okay, I'm saying it's cheap because the proof is very easy, but it's actually very expensive in the sense that it's hard to guarantee this condition for the Euler equations. But it turns out that there is a very nice application to the compressible Navier-Stokes equations, which do satisfy this divergence measure condition a priori. Okay, so we obtain a result for Navier-Stokes, and without such an expensive assumption on the velocity, if we revert back to Hölder spaces, then we can actually still guarantee energy conservation with vacuum in the range of adiabatic exponents between 1 and 2, at a slight cost of the exponents of the regularity exponents. Okay, which is to be expected somehow because I need to account for the fact that the pressure, that the density is only integrated with this exponent. Okay, I'll skip the rest. I should skip this as well. Let me just mention very quickly that those convex integration methods that I mentioned for compressible Euler, they always depend on the fact that you can somehow revert to the incompressible case. Because when you look at the compressible Euler equations, if you assume that the density is constant, okay, if you If the density is constant, then you really end up with incompressible Euler again. Okay, and this was the case already started by observation already started by Delelis and Sekilichidi. So if you take this convex integrated solution to incompressible Euler, append a constant density to it, you end up with a solution of compressible Euler. So the question was, there should be something more powerful, somehow a fully compressible convex integration scheme, and we looked at that with Jack Skipper and Emil Wiedemann, and it turned out that this is not actually the case, which is very surprising because so it turns out that any solution that is achievable by this convex integration approach is achievable so by doing oscillations in the velocity only. Which is weird because if you think about it, you can start with a small density, you add oscillations only to the velocity, and then you end up with something very irregular, which is irregular in both components. So that's a very striking property. So, okay, I'll skip the last thing, and let me just end up with a quote of Cédric Villani about those recent developments in the theory of Euler equations, and this is what Agnieszka called the golden age. If you read it, you can either look at it as something very exciting or slightly depressing. And that's you choose. Thank you very much. Sorry for going over time.
Thank you very much for your talk. Are there other questions?
Given the low regularity setting and also what you described in terms of Onsager's conjecture, does paradifferential calculus play any role sort of in
It does.
your proofs or in general?
Yes, it does. It does. So I won't give you any details, but we can talk about that.
Yeah.
Expression is linked by another theorem to symmetry time translation, and the system is invariant. So where this symmetry is lost in all this process? If we don't have energy conservation, we have to lose symmetry somewhere.
Well, the honest answer is, it's somehow still not very clear how the symmetry is lost, where exactly the energy is. That's very interesting. That's why those solutions that you obtain by this convex integration methods are, very weird objects. And they are actually called wild solutions because they come as a limit of this iterative technique when you add on oscillations, and where exactly physically the breakdown happens is not very well understood. It has to be, yes. Yeah. You mentioned the noise theorem, but I can't be more clear.
Obviously, another theorem also has some requirements on smoothness, and so it's not.
Yes, it's all related to regularity somehow,
yeah,
right? Because
obviously, irregularities should somehow be linked to loss of symmetry.
Yes, it's certainly another way of phrasing this. But I can't, point my finger to when exactly it happens.
Yes. So you mentioned vacuum here, which sounds like another topological thing that could happen.
Yes.
Is this known that it can develop vacuum, or is it an open thing?
It is still largely open to know whether. starting from generic initial data, whether vacuum will develop or not. It's not even known, I believe, for Navier-Stokes equations. So it's
Even not generic, but is there one example of developing vacuum? Is this possible?
you can think of data which sort of rips the fluid. So you have a current in one direction and in another direction, and then you do. So there are some results in this. But it's a very good question, because it's it's a degeneracy which is just of course. If you have enough regularity, then you can guarantee that if you start away from vacuum, you stay away from vacuum. This is just by looking at the continuity equation. Okay? But at low regularity, it's not guaranteed a priori for weak solutions. And yes, you can think of those.
So I suggest if there are any other questions, we will postpone them. Thank you very much.